Yeah, thank you very much for the introduction. And well, thanks to the organizers for making this conference happen, and also for giving me the opportunity to talk about quantum field theory. Actually, I'm not an expert in quantum field theory. I wrote more on classical general relativity, but I find quantum field theory very exciting, and so was very happy when Felix and Nikki offered me to join their research program, in particular because I already pushed it forward to some really exciting stage, and where I could skip all the hard work and just join for the really exciting times. So let me just tell you about these exciting times. So let's talk about well, the question: how does quantum field theory arise from causal fermion systems? Okay, so currently we have two different ways to build a connection between causal fermion systems and actually quantum electrodynamics. Okay, so the first approach is the construction of an algebraic quantum state. So we have seen that in Anna Falk's talk earlier today. So this is a construction of algebraic quantum states. That's a mapping in the space of observables to, well, expectation values. And this is built from causal fermion systems, this particular state. And this actually is a very general construction, works essentially for all causal fermion systems, pretty much. And it's general enough also to describe entanglement. Okay, and this research program on the first part of this first construction is due mostly, I mean, to Felix and Nikki. There's actually a whole sequence of papers that led to this work. So they put a lot of thinking into this, and yeah, I'll only show you the main paper about that. So reference to earlier work and also some other collaborators there. It's all in this paper, but I don't want to get into all these details. Okay, so this is the first approach, and this is a quantum state at a fixed time t. Okay, so the question arises: so how's the dynamics of this quantum state? How do things move? And for that, we have a second construction. And this, I would just think of this as a different construction. Of course, there are relationships between them, but just let's view that as a different construction. So that's the second part of my talk. That was some joint work with all of us, of four collaborators. And the idea is here to derive the canonical commutation relations of QED from the Euler-Lagrange equation of the causal fermion system. So that's the idea. And once you have the canonical commutation relations, then you can introduce, you can get all your dynamics from that, Feynman diagrams, and so on. So that's the goal here. How can you get the CCR, the canonical commutation relations from causal fermion systems? And this is a more general, more special setting. So it's more concrete. It makes use of stochastic averaging and of non-locality. And yeah, as I said, we get the dynamics here and Feynman diagrams. Okay, now for the rest of my talk, I will just go through these two constructions, showing you some more details, but I'll still be somewhat vague with some constructions, oversimplify a couple of steps, but I hope I managed to give you the main ideas of what these constructions are. So first of all, yeah, let's begin with the first point, okay? Number one. So the construction of the algebraic quantum state. So there should have been a reference here now. Okay. Maybe I forgot to update that. Sorry, so this is now the construction due to Felix Finster and Nikki Cameron. So, this quantum state here, that is a mapping from the space of, from the algebra of observables to the complex numbers. So it assumes values of expectation values. I mean, this mapping, the state. And it's defined by this formula, okay, by this path integral-like formula. Okay, and now I just want to explain what the different elements are, this formula. So first of all, what's in the argument? Well, that's an element from the space of observables. So it's an observable and emission operator on some suitably constructed Hilbert space constructed from causal fermion systems. Okay, now what is the state actually supposed to describe? Okay, that's of course an important question. So what's the setup? So the setup is that we consider two causal fermion systems. One describing the vacuum. So this is just the construction we have seen on the first day for how to construct a causal fermion system. Here's the untilted one from the vacuum Dirac equation. So that's the non-interacting background state around which we kind of perturb. Yeah, so that's the rho here, and then all the quantities with tilde, so the rho tilde, that's a different causal fermion system that describes interactions of some sort. This can be very general. It should be a critical point of the causal, so minimizer of the causal fermion system, or both are, but otherwise it's essentially completely general. Okay, and now what is the state doing? Well, this in some sense describes the, let's call it, excitations of rho tilde over rho. So it kind of compares these two, the content in these two measures relative to each other from the point of view of the observable here. So as tested by the observable or seen by the observable. I mean, it's a little bit of vague here. Okay, so that is the idea, that some of you describe excitation of rho tilde over rho from the point of view of the observable in the argument. Okay, so that's the left-hand side. That's what the state is supposed to do. Let's explain the elements. So first of all, I mentioned it's a path integral-like structure. What do I mean with that? Well, the idea is, again, you integrate over all possible configurations that you can squeeze into this causal fermion system. That's the idea, but actually the integration is not over passes of curves, so it's very different. This is actually integrate over unitary groups. So we integrate over the whole unitary group of transformations on the Hilbert space of the causal fermion systems. Okay, so it's of course very different. But yeah, where does this come from? Well, the thing is, we have two Hilbert spaces. Each causal fermion system comes together with a Hilbert space, H and H tilde, and you have a lot of degrees of freedom to identify those. And this unitary group describes the freedom to identify those Hilbert spaces. So that's how we integrate over them to really account for all possible configurations and possibilities to identify these two Hilbert spaces. Okay, so that's what we integrate over. Okay, so next object here. So what's actually what's the integrand? So here we have the gamma t, that is a certain surface layer integral, comparing rho tilde to rho at some fixed time t. So the time t is taken from the background measure. So it's Minkowski space, just standard time t we have here available. And we integrate over regions in the past of t, and then the complement of those, and so on. And this kind of compares that. And here we have the Lagrangian of the causal fermion system, okay? So that's the structure here. Now, zt is our partition function. So again, that's the idea. You integrate over all possible configurations. So again, this is essentially the same integral like this one. Yeah? So you see the state here, it's the same integral, essentially the same integral, and then you divide by that. So you normalize out all possible configurations. So now what's actually the main ingredient here? So the most important thing here is actually the one thing I didn't write down. Yeah? So the parentheses here with the dots, that's where all the meat is. Yeah? So that really makes a difference. So that here are the so-called insertions. So that's where the actual input from, well, the causal fermion system together with the observables. So here they are intertwined. So you intertwine the observables, causal fermion system. That's really where everything happens. And now this is I'm highly oversimplifying here, but so we have two types of insertions. First of all, the bosonic insertions. And what are those? Well, they're roughly derivatives of this gamma, the surface layer integral here, derivatives of the gamma with respect to the bosonic fields that appear in the field operators, in the creation and annihilation operators that make up the observable A. Yeah? So we assume, let's say A, the observable, is a product of different creation and annihilation operators over, let's say, bosonic fields. And then for each of these bosonic fields that appear in the observable A, you have to put in such a factor. And so your insertion is then a long product of these factors depending on which bosonic fields appear in the observable and not. Okay, so that's how you have to include those. And then you do the same for the fermionic fields. So the fermionic fields, the creation and annihilation operators that appear in A here. I didn't write down the formula, actually, I'm sorry for that. So you do the same, something similar for the fermionic fields, okay? This is actually a little bit more technical, and that's why I skipped it here, but the idea is somewhat similar, okay? Now, great, now we filled in what this is, and now we have a complete state here. And now, is this actually really a state? Sorry, is that the question? Yes, yes. Oh, I think that was a harm measure. Or do you remember, Felix or Nikki? Yeah. Okay. All right. Now I talk about states. Actually, to be a state, you have to be positive. Yeah. So I mean, not emotionally, but here you need to satisfy that here. The state better be positive if you apply if you apply the state to A star A. Okay, that better be positive, and yes, that it works out. So Felix and Nikki proved that this is always a positive state. So this is great. So it's really a state. Now, what about the meaning of the state? Is this just some weird construction, or does it have the right meaning? And yes, it actually has the right meaning. It really gives you the expectation value. Yes, you can introduce the expectation value of this observable A. So it means you can construct a suitable Fock space, and on this Fock space, a density matrix or density operator. And then the state really is identical to the Fock space trace over the density operator applied to the observable A. So the interpretation also, check there, it's also good. And now what about entangled states? Yes, you also get entangled states. So entanglement is also described by that. Up to the little caveat that you need a refinement of that state. So this state here is actually the simplest version of the state, the most elegant one. That's why I presented it here. But you actually have more freedom here. The integration you can put in the U not only here, you can also put in different places and use double integrals. So there are more complicated ways to mix everything up. And to really get into all possible configurations, you want to mix up the stuff as much as possible. Yeah, it's and that's what happens with this. That's what I mean with this refinement. So you have to go to a slightly more sophisticated version here, and then you can construct entangled states in that description. And that was then done in the second paper here. And by the way, I would say this is a kind of culmination that led to this formulation of a sequence of earlier works. So if you want to see the references to the earlier works, I would recommend this paper here, Felix and Nikki. Okay, great. So now we got an algebraic quantum state. Let's move on. How does that thing evolve in time? Well, yes. Oh, 5 minutes. Okay, not a question. Okay, 5 minutes. Okay, let's be more dynamical here. Okay. Sorry, bad joke, but okay. Let's how do we do that? Well, different setting here. This is we change the point of view. We go to a much more concrete setting. So we start with the Dirac equation over Minkowski space with some non-local potential. Yeah. So the non-local potential here, that is obtained from the linearized Euler-Lagrange equation of the causal fermion system. So Felix set a paper on that, I think 2 years ago or so, how these solutions look like, and a pretty technical paper, and we use that as a guiding principle for the modeling here. So we assume B is this non-local potential, so it's an integral kernel, and the integral kernel is of this form, okay? This here is a non-local linear operator. The A here, that is just it's a scalar field like the electromagnetic field. And the role of that is to induce defacing effects into the whole business here, just to drop that term. And B, that kernel here, that is what solves the linearized Euler-Lagrange equation of the causal fermion system. Okay, and now we have some here, and this is also important because summation is usually quite large. I mean, we sum over n terms, and the upper bound n here, that actually relates to, I mean, maybe I'm oversimplifying a little bit, but you can think of this to be roughly of the order of the length scale of the non-locality in L and the Planck scale. Yeah, I mean, there are actually refinements of that, but anyway, so that's where this n comes from, oversimplifying a little bit. Okay, and now what do we get? Well, if you average over that whole thing, I mean, like what people do with these collapse theories. So if you suitable average over that, so you assume these fields are actually of a whole family of fields over some averaging parameter, and you assume suitable relations, but very generic relations on the averaging. And then for suitable choices of these potentials here, well, within the solution space, you really get the canonical commutation relations up to error terms of this form, so of the form of the n here. So if we have a lot of terms, then the error becomes very small, and so we need a lot of terms here, and that's tied to the length scales. By the way, I also want to mention that the suitability of these choices, what I mean, I don't mean there's any fine-tuning here. This is very generic, so we just have to rule out some, just don't do anything stupid. That's essentially what it means. So that's so this is not fine-tuning anything. Okay, there's also the commutation relations. I just want to write them down. So you have the commutator of fields. I mean, they actually, I didn't explain what those are, but they're related to the integral kernel in a more complicated way. And if you average over those, then you get, well, here's this, the causal fundamental solution. This is, by the way, all in momentum space. So that's the one example of these commutation relations. Yeah, just to make it more concrete. Anyways, now to come to the conclusion here. So we've seen from this construction by averaging in a suitable sense and with generic choices for these potentials in the solution space, one gets really standard perturbative quantum electrodynamics. You can construct it. Once you have the canonical commutation relations, you can just do everything as always. So you get everything back as always, except for error terms of this form. And now this is, of course, really exciting because once you quantify these error terms, you have corrections to standard QED due to causal fermion systems. So hopefully testable predictions. So that would be, of course, amazing to get that. So that's what I find really intriguing about this approach, and that's what I'm very excited about. But anyways, thanks for listening, and yeah, thanks for listening.